We're
in the intense part of this.
yes. Okay, so let's recall. So how far did we get? We changed r hat of n several times. I think the latest version is something like, yep, exactly.
Yeah, exactly.
2/4.
And this is going to be the final version for us?
It'll be the final version for us. We're not going to go into more details of the
The
proof.
cascade of
That's right.
I looked at the paper. It's much scarier than what we are doing. It seems. Yeah, I was very discouraged.
Well, the idea, I mean, I can point you to where the ideas all are, but indeed, one has to do quite a lot more work than what I'm. This is the first version, right? And then you go to write the paper and you realize there are all kinds of problems. You have to fix those problems.
Right.
And then it becomes this monster.
And you have to try to write it compactly too.
And they have to write it in a way that people will understand, but also will,
That seems to be very difficult.
Yeah. So again, when we grouped by n to the half, the first time. This was x and this was y. And we managed to show that the supremum over theta in this WQK, just the L infinity bound, we got this n to the 2 delta over QK. And then there's some crap left over.
Right.
Okay.
It was like for major arcs and for like the large kappa.
The large kappa, exactly. This WQK, just to get it up again, is Q of size Q, A co-prime to Q, and beta of size K over N. Okay. And now we're working on the second Klusterman refinement. So we're summing Q of size Q, A co-prime to Q, and let's just call it Rn hat theta. But now we're going to decompose. You see, here we have room to do not just bilinear, but multilinear. This is linear in each of the factors. So this is a multilinear, not just bilinear.
Is multilinear in the same sense as determinate or something?
Multilinear in the sense that each of the variables, if you fix the other variables, it's linear in the remaining variable. So it's linear in gamma 3. If I take this and if I do Cauchy-Schwarz in gamma 3 or something, keeping the other two fixed, there's a gamma 3 minus gamma 3 prime sitting right here. Okay, and that's true for each of the variables. Even though it's really cubic as a function in the variables, now I have a cubic polynomial here. But with the variable, with the coefficients gamma 1, gamma 2 fixed, it's linear in gamma 3. So and that's the case for each of the variables. So we have this like at every stage, in every range, we'll have.
You running like experimental things for R and theta, like for that particular R and theta, do we know the actual growth, not the one that we can prove? Because usually we know what should be true, and we just are struggling to solve it.
Well, again, the picture is like this, right? It's something like this. So it still looks just like the plot of the real part, for example. And so, what do you mean by growth? I mean,
supremum, right?
The supremum in this range.
Yeah.
In this range. So, well, it depends, how do you see this? You have to choose your parameters of Q and N, so on this range, do you see that it's bounded by Q squared instead of Q or something? Yeah, experimentally, it's a very interesting question. I haven't tried to see what
parameters floating around.
There's a lot of parameters floating around, and it's pretty hard to tell experimentally as far as I can tell. Now, that's an interesting question. I haven't really tried. So can you tell experimentally what should be the truth?
Future research idea.
Yep.
Yeah, because we have this idea of the universe where, all the errors are good, and the universe where some errors are bad. It's
Yes.
in average they're good.
Yes.
And we believe that.
Yes. Individually. Yes. What can we prove individually?
Yeah, but anyway, I'm sorry. Okay.
So, right. So we're studying this. We need to save Q squared and a little bit more. Need to save Q squared and a little bit more. We need to get rid of these two sums and get a little bit more cancellation. We applied Cauchy-Schwarz in the X variable. X is the size of, we grouped, I don't know what we grouped. We grouped gamma 2 and gamma 3 together. into a variable of size n to the 3/4.
Oh, you mean for the low kappa case?
No, I'm no longer reviewing the low kappa case.
Oh,
I'm now
okay.
moving on to the, sorry, you're absolutely right. This was the large kappa case. This is good as long as kappa is large. Now we're in the low kappa case, and now we're decomposing y is n to the 1/4 and x is n to the 3/4.
Exactly, exactly. And seeing why this works.
Yes,
Okay.
and trying to prove that we'll get cancellation. So we get this x to the 2 delta, which just comes out from Cauchy-Schwarz. We get the x squared, which comes out from Poisson summation. And then we have a sum, over, well, there's z and z prime. These are pairs of integers of size y. They're primitive integers because they're, this is like gamma 2 v, and this was gamma 2 prime v or something. So they're primitive. And then a sum over q and q prime, both of size q. A sum over a mod q, a sum over a prime mod q prime, both co-prime. And then we got to this indicator function that theta z minus theta prime z was less than 1/x, as always.
You're saying at this point, we still haven't used this 3/4, 1/4.
We haven't used it yet. When we did use it was when we tried, our first attempt was to say, well, okay, as before, we had this a over q z plus a prime over q prime z prime. That's going to be bounded by, when you work this out, k over x. There's a 1/x from this, and then a beta times, and beta is of size k over n times y. And so we get this k over x. I'm just reminding you. But this is at least 1/q prime, which is at least 1/q squared. And this was no good. We got no cancellation.
No 1/2.
Got no contradiction. Yeah, from the if non-zero. This is the if this thing isn't zero.
Right.
So no contradiction. I'm just reminding you. So then we had this great idea is to look at instead this a over q z, where z is the determinant, z1, z2, z1 prime, z2 prime, is to play the two. This is really a two-dimensional vector. We played this against itself. We saw that this was bounded not by k over x, but k over x times y. But if non-zero, if this thing is not zero, this would be at least 1/q. And so if we can make y over x equal to n to the 1/2, which is exactly why we chose y to be n to the 1/4, n to the 3. So y is n to the 1/4, x is n to the 3/4. Then we do get a contradiction.
Then what were the issues with us? To understand z better.
Yes, well, let's see how much we've saved. So what we found is that z has to be 0 mod q, since a and q is co-prime. So this is indeed 0. So z is 0 mod q. By symmetry, z is also 0 mod q prime. And so in fact, z is 0 mod their LCM. So this is the LCM of q and q prime. Okay, so that's as far as we got. And now we need to get cancellation out of this fact. Okay, so first of all, observe, let's write this in another way. If I fix z1 and z2 so that I have this z, then q actually has to be a divisor of z.
Can you repeat this?
Yes, so I have my variables here floating around. There's a z, z prime, q, q prime, a prime. In what order do I want to move them around to get cancellation out of this condition? So this condition we've seen implies, with this choice of parameters, y and x, implies that z is 0 mod the LCM. So if I fix z and z prime first, then the LCM is a divisor of this z. And q is a divisor of q, and q prime is a divisor of q. So that this is going to save us. This saves. In other words, how many divisors are there? What's the size of the divisor set? How many divisors does a number of size n have? Very crudely. N to the epsilon. Okay, so there's no, it's like 1. So now Q and Q prime are basically determined. So instead of having a sum over Q and Q prime, asymptotically determined. So this saves a whole factor of Q squared.
Wait, but I don't think I was getting why Q has to divide Z.
Z is 0 mod Q.
Okay, Z,
Z is a multiple of Q.
and it had to be a multiple of Q, why?
Because, so Z is, so we saw that this A over Q times Z
Yeah.
must have nearest integer 0.
Oh, that's nearest integer. is
Yes.
what that, oh, we're doing.
Yes, this is nearest integer.
Oh, okay, and that's why,
Distance to the nearest integer.
right, and for that to be 0, then it has to be 0, 1. Okay. And then
Okay.
you're saying that,
So that was for little q. Run the same argument, you get it for little q prime.
yeah,
Well, then let's call frac q the LCM, then it's
Okay.
0 mod the LCM.
yeah, now I'm good.
So the LCM is a divisor, and of course, q and q prime divide their LCM. So we've saved a factor of q squared, because there's no longer a sum over q and q prime.
Oh, right. So
Those have been reduced to,
Those would normally be like Q squared.
those would be q each, yeah, there'd be a q here and a q here, but now there's 1 and 1.
Q to the 2 epsilon or something.
We need to save a little more, but there's something wrong with my argument.
Okay.
There's one little hiccup. You have to remember the Alamo. You have to remember the diagonal. The diagonal is when Z is equal to Z prime,
Mm,
in which case this determinant is 0.
yeah.
And if the determinant is 0, the fact that Q divides 0 is not a restriction on Q at all. Every number divides 0.
That's true.
Okay, so it doesn't save, it saves Q squared as long as Z doesn't equal 0. Okay, so
And then like on top of that, like, they don't even have to be like identical columns for this to happen, right? It can just be some other freak condition.
there could be a freak condition, you'll see in a second, yeah, but certainly if this number is non-zero, then we do save Q squared, because there's a
For sure, yeah.
because there's a restriction on division. So we have to decompose this sum according to whether whether this determinant is 0 or not,
Right.
Okay.
Yeah.
and then handle the two cases separately.
And the idea is if you have determinant 0, then that should give you some extra information, right? So,
Yep. So we break the sum on Z and Z prime according to, well, I guess it's literally equal. Z and Z prime is equal to a sum over, I'm so used to putting an inequality that I don't even, this is going to be an exact decomposition. This is where Z is not equal to 0 plus where it is equal to 0.
exactly.
Of course, either one or the other happens. We're not in this law of excluded middle situation. But since everything's an upper bound, I just can't help myself. But
And the Q squared savings, is that good enough for our purposes?
we need more.
We need more.
We need a little bit more than Q squared. We needed a little bit more than Q before we Cauchy-Schwarzed. Now there's a square here,
okay,
so we need a little bit more than Q squared.
Interesting. Okay.
Sorry, I think what I said before we squared. What I meant to say, because the length is Q squared. We're not trying to save the length. We're trying to save the square root of the length. The number of terms here is Q and another Q. So the length is Q squared. We're not trying to save Q squared off of this inside sum. We're only trying to save Q off of it. But when we square,
Exactly. Then
saving
you
Q off of that is the same as saving Q squared off of the square,
have- Right.
plus a little bit more.
But then
Okay,
you're expanding the square, right? So you have to take.
right. All right. Well, let's continue with this Z not equal to 0 case. We've already saved Z squared. Let's try to finish it. What more is there? So let's consider case Z not equal to 0. Okay. Well, if Z is not equal to 0, then again, we've saved, then Q and Q prime are determined once frac Q is determined, which is determined basically by Z. Let's look back at this condition. So now we have that Q, so the fact that Q, this frac Q divides Z and Z is not equal to 0 means that frac Q, of course, is at most Z.
Yeah.
But what's the size of Z? Z is quadratic in our variables, which are of size Y. The little z's are of size Y.
This is like y squared.
So it's like Y squared. Q is also at most, Q is the LCM of two numbers of size at most Q. So this is also at most Q squared. Okay, so if I multiply these two, then I get Q squared is at most Y squared Q squared. In other words, Q is at most YQ. Okay, but let's go back to this condition. This condition, we tried this lower bound and we got nowhere. We got nowhere because it's really not QQ prime, it's the LCM that's here. And that LCM could be as large as Q squared. But now we just got a better bound on the LCM. It's not Q squared, it's YQ. So look back at A.
Of about size what?
Which Q? The little Q?
The big Q.
Big Q?
Yeah,
Big Q is of size anything n to the alpha, where alpha is a little bit large,
a little bit larger.
like
right?
bigger than alpha 0, which is microscopic.
Exactly, so, okay.
So in our picture, we're worried about,
Non-trivial alpha.
Yes.
Is,
yes, this range of alpha.
Exactly.
How big is Y? Why is it about?
To 3/4?
Y is n to the 1/4.
1/4.
Okay, how big is N?
N is just our growing parameter. M is the main parameter, little n is of size capital N.
And so I guess I'd think that one of either Y or Q is smaller, and I can just pick that one.
Okay, so,
What's
yes.
What's the upside of?
yes, it's the minimum. So so this frac, you'll see in a second, this frac Q is less than the minimum of Y squared and Q. So we're doing something crude by saying it's bounded by YQ.
But YQ is better than maximum, that's all we need.
YQ, you'll see in 1 second where this YQ will play a role. So if I go back to this bound, and we had this bounded by K over X, right? And we said that this is at least, if non-zero, so if non-zero, if this thing isn't 0, this distance to the nearest integer isn't 0, then this is bounded by 1 over QQ prime, but really it's bounded by 1 over Q, the LCM. But now the LCM is not of size 1 over Q squared, it's of size 1 over YQ. So look back at this condition. It says that if I multiply through,
Y over X, you know.
we know that QK is less than n to the 1/2.
Yeah, so it is X over Y smaller than QK, and X over Y was N to the 1/2.
Exactly. And this is n to the 3/4 over n to the 1/4, which is n to the 1.
Bounded by a constant?
Yeah, you need some, again, as always, you have to play with the constants. You add some factors of 1,000
Oh,
here and
no,
there.
what I mean, I guess, is that Y over X n to the 1/2, and then K times Q also n to the 1/2, so.
So this is just enough to Nick's question, why do I care about this? This is just enough, this is exactly what we need in order to be able to get the contradiction. This gives us our requisite contradiction because 1 over Y, if I divide both sides of this, in other words, I mean, just look here, K over X, let's turn this around. This implies that K over X needs to be less than 1 over YQ. And here I'm saying 1 over YQ is the lower bound for this thing, which is at most K over X.
So where do we get the QK less than N to the 1/2?
That's in the Dirichlet approximation theorem.
Okay,
In Dirichlet approximation, we have two conditions.
okay.
Q is less than n to the 1/2, which was our parameter M. From the,
Implied is throwing me off. Looks like that one's.
Sorry.
That's all good. Okay, I see.
Okay, so then,
so now we do get the contradiction.
but then how do you deal with the constants?
As always, it's by breaking the z's into little rectangles. This is what,
Because you gotta make sure that, like, Okay, these are of the same order of magnitude, but it is possible for a certain choice of constants that this still works, right?
Yeah, so this will really have a factor of 1/1000 in it from the fact that the z's are close
Oh,
together.
I see. And then that way, like, then you actually get.
Then you actually get a contradiction.
Wow, it turns out to be kind of tight, right?
I mean, in terms of the growing up parameters, it's
Right.
tight.
Yeah,
In terms of the constants, you have room to play.
yeah, exactly. Yeah, like asymptotically,
Yes.
these are of the same order.
Yes,
right? So
they can be, yeah, they can be. Exactly. So what this tells us is that the distance to the nearest integer of this thing is 0.
Right, given the contradiction, yes.
Okay, so in other words, a z1 over q is congruent to a prime z1 prime over q prime mod 1. Okay, let's go into, so we've written q, this frac q, as the LCM. Let's go into this condition. I don't know, what should we call it? Q tilde. Q tilde be the GCD of q and q prime.
Oh, and this Q, this frac Q is what's connecting us to this weird determinant. Right?
It's a divisor of the weird determinant.
Which is why, like, so is this gonna be our bridge between the determinant? Is this how we're gonna use a determinant to conclude this case, or?
No, we've already gotten as much as we're going to get out of this determinant. In other words, that we've saved q squared. Now we want to save just a little bit more.
That's what I mean, yeah. So we're done with that Z.
We're done with that z.
Okay,
We've used it to bound frac q.
exactly.
That frac q gives us that this actually is 0.
So this is, okay, yeah.
And now we want to convert this into something that we can work with.
Exactly, okay, yeah.
Okay. So if we let q tilde be the GCD and write q as the GCD times something like q1, I just want some variables to know what the decomposition is between q and q prime. Q prime will be the same GCD times some q1 prime. Of course, q1 and q1 prime are co-prime.
Yeah.
Right, so I'm just pulling out the part that they have in common.
Right.
And then what is the LCM? The LCM is q1, q tilde, q1 prime. Right, this part of the LCM is q. This part of the LCM is q prime.
Right, yeah.
Okay, I haven't done anything. So I want to turn this condition, let's multiply this condition by I want to clear the denominators. But I don't want to multiply by q prime, I want to multiply by the LCM.
Yeah, right.
Okay, so clear denominators. Clear denominators. And mod q tilde, so I have to multiply this by this, which is q1 q tilde q1 prime. So here I'm going to get a z1 q1 prime is congruent to a prime z1 prime q1 mod the LCM.
Wait, there's something weird going on here. Like you have q and q prime, and then you have the q1 and q1 prime.
Yes.
How are you getting rid of the q and q prime?
Because I'm multiplying
Oh,
everything
yeah.
by frac q.
Yeah, I mean, so.
Yep. So I'm canceling off this. All that's left is the q1 prime.
Right, yeah. That's totally right.
And then when I multiply on the other side, all that's left is q1.
Yeah.
Okay. Let's reduce this equation mod q1. So look, mod q1. What do you have? You have a z1 q1 prime is congruent to 0 mod q1. Q1 is a divisor of this frac.
Mhm.
But A is coprime to Q. A is coprime to Q. And Q1 prime is coprime to Q1.
So you get z1 is 0.
So you get Z1 is 0. So you get Z1 is 0 mod Q1.
But also mod q2
Z,
or q.
Z2 is also same argument.
Yeah, exactly.
Same argument implies that Z2 is congruent to 0 mod Q1. But what's wrong with that?
So
This is a
now
Q1.
Z1 and Z2 will be
Remember what Z was. Z is gamma 2V. It's a matrix in SL2Z, a row of a matrix of SL2Z, and both entries are divisible by Q1.
So all of a sudden, this isn't like an SL2Z. Wait, no, but, yeah.
It wouldn't be. The only way this is still going to be an SL2Z is if Q1 is equal to
You have some sort of 0 and.
Q1 has to be 1. Q1 is a divisor of Q,
Oh, right.
right? What does it mean? Z1 and Z2 have GCD 1, and we found a divisor of both of them.
Right.
Well, that divisor has to be 1. Right? But GCD of Z1 and Z2 is 1. It's a primitive vector. Z is a primitive vector. So Q1, in fact, has to be 1. Now we run the same argument. The same argument implies that Q2 has to be 1. What does it mean that Q1 and Q2 are 1? Sorry, Q1 and Q1 prime. Sorry.
I mean, that's gonna give that now. Right, Q and Q prime are the same.
Are the same.
Yeah.
Nick, did you? I went too fast somewhere.
Okay, so I'm lost is, where is Z2 doing this whole time?
So
Just appeared, okay.
there has been no Z2. We were just working with one component.
Right.
We were only working with the Z1 component of this inequality. But we have this inequality both for Z1 and for Z2.
Okay, and.
So out of nowhere,
Oh, and that inequality only has a Q and a Q prime. Q1 was defined separately. Q1 has nothing to do with C1.
that's right.
Those index ones are not. Okay.
They're independent of the Z's.
Totally run the same argument. Okay.
Totally run the same argument, and you get it for Z2.
Yep, C1, Z2 are co-prime. That's fine. So that gives Q1 is 1. Do the same thing. Where's Q2 sitting?
I'm sorry, not Q2, Q1 prime.
Okay.
Yeah.
Then I'm all good.
Right? Just run the symmetric argument.
Maybe Q2 is somewhere. Maybe. Maybe not in this part. I can't remember.
You know, you make up the variables as you go along, and then you just have to live with them.
Okay, somewhere I've written that the frac Q is LCM of. But here I have Q and Q1 and Q2. Other place I have Q and Q prime. Okay.
I've tried to consistently use Q and Q prime.
All right, somewhere else.
I may have failed.
I have a Q1 and Q2. Is that we're at case Z not 0? Where is that part of the notes?
Casey, yes.
Or did I write something funny? Might have been me that wrote something funny. Okay.
I only see Q and Q prime.
Well, I don't see it on your page, but I do see it on mine.
Okay. All right. Well, hopefully that's.
Must have been me that wrote it wrong.
Yeah.
Okay, good now.
And then like what you're calling the symmetric case is that this is mod frac Q, and then you're just choosing to mod by either Q1 or Q1 prime. Is that?
Yes, exactly. We modded by Q1, but we could have modded by Q1 prime and gotten exactly the same argument.
And then this, and Z1 and Z2 are also controlled by the same frac Q.
Z1 and Z2 are chosen first.
They're chosen first.
In order to
and
be in
then
the
we
case,
get it.
yes, in order to be in this case, we have to fix Z1, Z2, Z1 prime, Z2 prime.
Perfect. And then we get like, and that's when we start doing like our.
And that's when we
frac
start
Q
doing all of
results.
this. Exactly.
And so since this is the same frac Q, then it's like, it truly implies the same thing for the same modulus.
Yep.
Z1 and Z2.
So how much has this saved us? The fact that Q and Q prime are not just some random, they actually on the nose have to be the same, or otherwise there's no contribution.
That's like one other order, right? Like Q again?
Well, we already had, they were, we'd already crossed off a bunch of them anyway.
They were both gone already. We get no extra savings from this because they were already a divisor sum.
Yeah.
This does not give us any extra savings.
Simplifies the sum, I guess.
It simplifies things, but no extra savings. No extra savings, already had had that they were divisors of this Q, of this frac Q,
Which is already not.
and frac Q is already a divisor of Z, and Z is not equal to 0. Okay, but you see, I'm trying to show you, you just have to keep fighting this thing. Let's go all the way back here. Yes, if Q and Q prime are the same, then we get that A Z1, what do we have here? A Z1, this is 1, is congruent to, by the way, if they're the same, then their LCM and their GCD is the same.
Right.
So this is also equal to frac Q. So now I have A1 times 1, A1Z1 is AZ1 times 1 is congruent to A prime Z1 prime times 1 mod the 1Q. There's only 1Q floating around.
Yeah.
So this determines for Z1 prime and A fixed, for fixed A, for fixed,
Determine A prime.
it will determine A prime. It'll almost determine A prime. Z1 prime might have a large factor in common with Q. For fixed A and Z and Z1 and Z1 prime, which were already fixed from the beginning, and these guys, this determines A prime modulo whatever Q divided by the GCD of Q and Z1 prime is.
Exactly.
If these guys have a large factor in common, I can't tell what A prime is. But if I divide out that large factor in common, now I can invert, and then I can invert what's left.
Yeah.
But I don't know how big this is. But the same equation applies with 1s replaced by 2s. We also have AZ2 is congruent to A prime Z2 prime mod the same Q.
Yeah.
And so A prime is also determined mod Q over the GCD of Q and Q2 prime
Yeah, Z1 prime, Z2 prime
are co-prime, but Z1 prime and Z2 prime are co-prime.
One of them is gonna.
Well, it doesn't have to be, they could each have a factor,
Yes.
different factors in common with Q, but we've completely determined A. These two residue classes together, because Z1 and Z2 are co-prime, determine A mod Q, A prime. A prime is completely determined
Chinese.
mod Q by Chinese remainder. That's our last savings of a factor of Q. Right? Instead of having a sum over A prime, there's only one contribution to A prime. So instead of Q, this saves our remaining needed extra factor,
So A was originally of size what?
Q. A and A prime range mod Q.
It would range mod Q, but now it's only one value.
Now there's only one value. So instead of having Q values, now it takes one value.
Oh, I see. So that's another thing.
Okay,
Wow. Yeah.
let's put everything together.
So you're using these, okay, so you're saying you're determining it mod two numbers that are relatively prime to each other. It's Q over GCD QZ1, Q over GCD QZ2,
Yes,
and then Chinese remainder will tell you
that we know what it is mod Q.
mod Q because, and not a lower confluence.
Right. But these numbers are relatively prime.
Against working like this to
That's a good stuff.
narrow down how to
It's a good stuff.
this contribution.
Analytic number theory.
Yeah.
Amazing to do this much to it.
No, this is great. Yeah, you build up all this theory, and then in the end, you're doing the same stuff the undergrads do.
That's why we need the undergrads to know this stuff.
Yep.
Let's summarize. We took the part, where were we? We had this sum on Z and Z prime. We broke it into whether this determinant is 0 or not. There was a factor of x to the 2 delta times x squared out front of the Cauchy-Schwarz. So, well, let's save that factor for later. The part of the summation, the Z prime with Z not equal to 0, we have bounded by. Okay, so and then everything else. that I didn't put in here. We've bounded by, you fix your z and you fix your z prime subject to this determinant being not zero. Then you find your favorite divisor of z of this determinant. Once the determinant is fixed and it's not zero, you sum over the possible divisors. From those possible divisors, you sum over possible values of q. And by the way, that divisor will be less than yq. You sum over the possible values of q, and q prime will be equal to q. This q is at most q. Then you sum over a mod q, coprime. And then you sum over a prime mod q, same q, coprime, but the a prime is determined. A prime is determined. And everything else we've gotten as much as we can out of. So this has one value. So now we bound everything from the inside out. There's one value of this. How about this guy? Q, nothing I can do about that. Q. How about this?
This is the n to the epsilon.
N to the epsilon, divisor sum. How about this?
Again,
N to the epsilon. How about these two?
the z's, or the q squared or something?
The z's were of size y,
Oh, so y
but they
squared.
can't, it would be y squared, and we can leave it as y squared, but let's be just a little bit more delicate with this. They actually came from the group. So it's not y squared, it's y to the 2 delta for each of those. So we get a y to the 2 delta.
That's how we bounded stuff in the group.
Yeah, the number of points in the group is y to the 2 delta.
Right.
Okay, so we get one for both of them. The fact that z is not equal to 0, we can't catch cancellation in that. That's too. Almost all the values do not agree. Okay, so what should have been y to the 4 delta from these, and then q to the 4th from q prime a prime is a q and not q to the 4th. So we've saved q cubed. We've saved a total of q cubed
In the squared version, right?
in the squared version, which is bigger than q squared. So we should be happy with this. We'll put everything back together.
Oh, okay, so then the n to the 2 epsilon goes into
Yep.
this q cubed bigger than q to the 2.
Yes.
something, right? It
Yes,
doesn't matter because you save an entire power over.
yep.
Wow.
Okay, that was case 1.
Right, now we need a determinant 0 case.
Case 2, when the determinant is equal to 0, so we don't get any, we are back to square 1. We have no cancellation in the q's. Okay, so case z is equal to 0.
You already said the y to the 2 delta.
Yes.
0.
Yes, yes, yes. So case z equals 0. Okay.
In a sense, would you expect, how often would you expect this determinant to be 0? Seems like probably pretty often.
Let's see right now. So what is the determinant? Z1, Z2 prime minus Z2, Z1 prime is equal to 0. In other words, these two things are equal. Well, that means that the fractions Z1 over Z2, if I cross divide, is equal to the fraction Z1 prime over Z2 prime. But the numbers are co-prime.
What numbers are?
Z1, Z2, it's a primitive vector.
Right, so this is reduced.
So they're both reduced. And so Z prime is equal to Z. So the only way that you get these two to be equal is on the diagonal. The only way this determinant can be 0 is when Z prime is literally equal to Z.
Oh, I see. Okay, so this does limit things quite a bit.
It limits things quite a bit. And exactly as Nick said, this saves one of the y to the 2 deltas.
By just having them be the same.
Because once Z is fixed, Z prime is determined. It's forced to be Z. Now, how big is that? Y to the 2 delta, remember y is n to the 1/4. So y to the 2 delta is n to the delta over 2. And n to the delta over 2 is not even, this is not even n to the half. And we need to save q squared. We need q squared savings plus a little bit more, which could be, depending on q, as large as q goes up to n to the 1/2. This could be as large as n to the 1.
Right. We say barely under a
We
half.
we barely saved under a half, and we need to go another n to the half and a little bit more.
And delta, what was delta again? So was this just controlling the growth of the group?
Exactly. And we're going to take it near 1. You think of delta as being close to 1. That's the Hausdorff dimension.
Oh, right.
Of this
And we were with these
Cantor set.
alphabets and whatnot. And you
Exactly.
can, like, push it. Yeah, okay. Back on track.
Yep.
Nice friendly 1 minus epsilon.
Exactly. Okay. So what are we going to do? Where are we going to get this extra cancellation? So the fact that this frac q divides 0 gives us nothing. The fact that, so we no longer have this savings, but we still have everything else. So if the two are equal, let's go back here. If the two are equal, we have this condition a over q z minus a prime over q prime z prime. Well, let's remember what we had. We had, this was less than or equal to theta times z minus theta prime times z prime plus beta times z minus z prime. Right? This was the condition. But z is equal to z prime.
All of a sudden, wow. Oh, no, this is the angry.
So this is nothing. This is 0. There's no change in the betas. This is bounded by this. We already we're in the range where this is bounded by 1 over x. And now let's look here term by term. So if I look at the first one, like a over q z1, so I can pull out this z1. Let me leave it in both places for just a second. A prime over q prime z1. Okay, this is bounded by 1 over x. Where I need to try to get cancellation, let's say we fix this fraction, the value of this fraction, let's call this, I don't know, psi. In other words, we fix, i.e. fix z1, fix a prime, and fix q prime. Okay, what we need to get is cancellation in the fact that this fraction has to be so close to this fixed value. Need to restrict how many possible values there are of a over q z1 so close, that are so close to this fixed value psi, a prime over q prime z1. Okay, that's the only place we have left to get any cancellation. There should be very few values in this range. If z1, let's get a let's do a little back of the envelope calculation to see if we have a chance. Back of the envelope calculation, to see if we have a chance. If we have a chance. Let's say that z1 and q are coprime. Say z1 and q are coprime. Okay. Then what's the mesh of the set of values that this takes? So I'm looking mod 1. So here's 0, 1. There's some fixed value psi, wherever that is. There's a range of size 1 over x around psi. And when I want to find how many possible fractions there are here. As A and Q range over different values. So how many possible fractions are there? Well, what's the difference between two, the mesh size is roughly of order for different values of A and Q. These fractions will be of size, will have differences between consecutive fractions. Will be of size.
1 over Q.
So there's a Q and there could be some other different values of Q. In other words,
Yeah, Q also, right?
yeah, A and Q range. Yeah, 1 over Q prime. Maybe now we need a Q2 or something. Yeah, so it's Q prime. So it's like 1 over Q squared. Okay, so if that's the distance between points, if that's the distance, this is the distance between consecutive points. So how many points, the number of fractions, this is the distance, to nearest neighbor.
The interval has size what?
Among A, yeah, the interval has size 1 over X.
So it's many 1 over Q squares you can fit in.
Values, yes. So how many, the number of values that we can fit is Q squared times 1 over X, exactly. Okay, but what is that? That's how many, once we fix one of those values, then we know, since A and Q are co-prime, we know what A is, and we know what Q is. We know what the denominator is and what the numerator is. Each such fraction determines A and Q. So what should have been Q squared, there's Q squared values. Now we've saved X.
X is to the 3.
X is n to the 3/4.
And then Q squared is in the end.
Right. So which should have had Q squared values. So this saves, if we can get this to work, this saves X.
Right.
And X is n to the 3/4. And this X together with what we've already saved, which is y to the 2 delta, is more than enough to push us over 1 plus something.
And we're getting this because these z's are equal, right? Had they not been equal, then the counting wouldn't have worked.
Well, if they had not been equal, so regardless of whether they're equal or not, we're fixing this value. And then we're looking at these possible values. Even if they weren't equal, that we would still fix this value and look at the mesh of these possible values and try to get cancellation. It wouldn't be enough if we didn't also have this y to the 2 delta. We would only get n to the 3/4. We need to go potentially as large as n to
This
the 1.
bottom saving would always happen if we did the analysis this way.
Yes.
But without y to the 2 delta, it doesn't push.
Yeah, exactly. Pushes us over.
Oh my gosh.
Okay. Now, what's wrong with this argument? It's that we don't know that Z1 and Q are co-prime. So we have to catch that. Okay. Sorry?
Yeah, like end to 1/4 wiggle room.
We got plenty of wiggle room. Yes.
And
This.
also, like, there are not that many things they could share, right? Like this is limited by the divisors of Z1.
Exactly.
And that's like another n to the epsilon.
Yep.
But we lose end to the epsilon.
We can afford to lose n to the epsilon because we're going to gain much more than that.
Right.
Okay. So let's do it for real. So now for real. We have, having done this back of the envelope calculation, we are energized to try to push it through with the details. So yes, we will fix this Z1, A prime, and Q prime. Now, we'll want to catch one of these denominators. You see, if the denominators are as small as possible, then we get to, then the mesh is smaller. And the smaller the mesh, the fewer points. So we want to make the denominators as small as possible. So let's assume that, okay, let the GCD of Z1 and Q be, I don't know, V, and let the GCD of Q with Z1 prime, sorry, there is no Z1 prime, it's Q prime. Z1 is the same, with Q prime be V prime. And let's assume that V prime is the largest one. Yeah, let's assume V prime is the larger one. Okay, so write Q as V times R. Okay, Q has V as a GCD, R is co-prime to Q. R is co-prime to Z1. Assume V prime is the larger one. I didn't finish writing. Assume V prime is the larger one. Okay, this is without loss of generality.
Right.
Otherwise, you order them the other way. Okay, so R and Z1 are co-prime. So I can write this equation. This equation becomes A, oh God, something over R, A times, okay, let's say Z1 is equal to V times
Write
B.
it all out.
Yeah, A times B. B is fixed. B is fixed. V is fixed because V is a divisor of Z1. V is a divisor of Z1. V prime is also a divisor of Z1. And we've assumed V is bigger than B. V prime is bigger than B. So we have this A times B over R. R is co-prime to B. So since B is a divisor of
Oh, you're saying for real, because this will also, if this works, it also knocks out the other case as well. Relatively prime case.
yeah, so this was all the back of the envelope calculation, assumed we were in this perfect world.
Right.
But now let's do it for real.
Okay, okay.
So for real, we have to take care of what the possible consequences are.
Right.
Okay, so now all of these fractions are reduced. And the distance to this fixed number psi is bounded by 1 over x. That's exactly this equation here. So far, so good? Okay, so now for real, how many, so the mesh is of size what? Well, there's 1 over R times R prime, right? Of these, so look at these fractions. Look at the set of A times B over R minus, well, just look at these fractions, A times B over R. As R ranges, R is of size what? R is of size big Q over V. Big Q over V. A is of size Q, and A is co-prime to Q, and in particular, co-prime to R. And B is also co-prime to R. But B is fixed. B is fixed. Okay, so the A is ranging and the R is ranging. The R is ranging in this range. The A is ranging mod Q, so the A is mod Q, and it's co-prime to this denominator R. Okay, so these points, exactly as we said here, these are some points. And the mesh is of size 1 over R, R prime. That's the closest two of these numbers could be together. And so this is at least V squared over Q squared. So the number of such fractions number of such fractions within 1 over x of this fixed value psi is, so the number of such, let's use math instead of words, is at most 1 over x is the length of the interval, and the mesh is this, so there's at most q squared over v squared of it.
And then V was fixed or something?
V is a divisor of z1,
So that's like
n to the epsilon.
to epsilon.
I mean, this should finish it, right? Because you compare to the epsilon and the other one like the previous one.
That's right. I'm waiting for someone to correct me.
Okay. Let's see, this plus one again.
Ah, yes. Yes, the killer of all arguments is the plus one. Now, in this case, I can't get rid of the plus one. This is of size n to the 3/4. This is of size, it could be of size n to the 1, but it could be much smaller.
Oh, I see. In the case that Q were small.
In the case that q squared over v squared, they're going to have a large GCD, is less than 1 over x, is less than x. This thing is less than 1. And I might be fooling myself and saying there's so few points. No, there's 1 point. There could be 1 point by accident in that interval. Okay, so do not forget the plus one. So many great arguments that are inside this subtle computation somewhere. When you count, always worry about a plus one when you count like this. Okay.
Why is the plus one gonna bother us?
Well, it may not save enough. So let's see in the end what we've saved. Okay, so let's do this for real. So let's go back to this summation, z and z prime, where z is equal to 0. So summary. We have a sum. This is the case that z is equal to 0 with everything else. What's it bounded by? Okay, we have a sum over all z, and z prime we just said is determined by z. So maybe to make the point, let me z prime is equal to z, so it's determined by z. Okay, then we sum over the divisors v dividing z1. Then we sum. Now let's be yeah, I think this will be good. Then we're going to sum over q1. Right, let's go with this, and then we'll see if this works. Q is of size q. A prime is co-prime to q prime. Once we fix z, a prime, and q prime, once we've fixed z, a prime, and q prime, psi is determined. Okay, so this base point is a prime, psi is equal to z1 a prime over q prime. Okay, so psi is now determined. It's a prime over q prime z1. Z1 and z2 were fixed here. So far, so good. Then we're going to sum over possible values of these fractions. So let's call these fractions. Let's give these fractions a name. What should I call them? I'm running out of f. So this is the set f, and a typical fraction in here is f. Okay, so we'll sum over fractions f in f. The number of such fractions is this. So the size of this is this. Once we've determined a fraction, that determines the numerator, and it determines the denominator. And so R is determined and A is determined. So a sum over R and A, which are determined by the value of f. Right? You buy that? Once you have the fraction is in lowest terms. And so that tells me what R is. R determines Q. R, and then of course Q is equal to R times V.
Again, is determined, right?
Is determined, yeah.
So three sums from that sum business are determined. C equals C prime and the last two.
They're determined but we have this at the cost of this. They're determined by the value of f, but how many f's are there? There's q squared over x. Here's our 1 over x savings.
Yeah, what I'm saying is that if someone tries to actually follow the sum and start summing things, once he has chosen an f, there's no summation happening. You just have some.
Exactly. These are both 1. Yeah.
Yeah,
So
in the same sense, C prime equals Z is not the J sum.
exactly. This is size 1.
Yeah, yeah, but I guess that's like.
I'm just spelling everything out.
No, it's very good, it's very good. I'm just saying that it's not, don't have what, 7 sums. We actually don't have 7 sums.
We have much less.
Yeah,
But that's like if we're paid with that loss of the one.
yeah.
right?
Exactly. We're going to see that in a minute. Okay.
More intimidating if we have 8 sums.
It looks more intimidating if we put all these. Yeah. I don't know of a better way. People write these things in words. We're sort of not at the stage where we have good notation.
If someone walks past the faster and glances at it and sees this.
Yeah.
Yeah. Sees this whole. Yeah.
Yeah, exactly. Be like,
Walking.
oh,
Right.
you wanna be my student, watch this video.
Oh God. Yes. This one in particular, where we're like deep in the weeds. Okay. So what do we have here? This is 1. There's exactly as Lena just said, there's no contribution here. The R and the A are determined by F. So there's 1 contribution here. How many elements are there here? 1 over x q squared over v squared.
Wait,
plus
can
1.
you explain it from the +1 business? I don't think all this time, I still don't think I get why
Yeah.
we need to from the +1.
Let's say that the mesh is so small that really what it looks like. Okay, so let me redraw the mesh. Here's
Would it
0,
mean that
1.
there are no points?
Well, it would mean that the number of points you expect to find here, if this length is 1 over x, but the mesh is so large that the distance between consecutive points should be larger than the length of the sum. But there might still be 1 point that's just sitting inside by accident. It's like
But not 2 points.
it's like how many numbers between -20 and 20 are 0 mod 100? Well, 100 is a bigger interval than -20 to 20. So there should be 0 points.
Yeah, but.
Except by accident, 0 is 0 mod 100. So 1 point gets in there.
Okay, so that's the same thing.
That's the same
what's
thing.
going on here. Okay.
So your estimate for roughly how many points there should be in any interval is way off from how many is missing the fact that there could be 1 point in there by accident.
Yeah, but then like if you had the sum of the +1, then you don't get the savings, but then at the same time, this restricts you very heavily.
Yes,
And then we should be able to get more out of that.
exactly.
Okay.
Okay, so how many A's are there mod q prime? Nothing we can do. There's q of them. How many here? Nothing we can do. There's q of them.
And we absolutely, into the y, no, y to the.
Y to the epsilon, but y and n are comparable, so we can be crude. And to the epsilon.
Yeah, of course.
And then here's a y to the 2 delta. So in any case, we have saved y to the 2 delta. And if there's a 1 here, then we've saved a q squared. So we've saved q squared and this extra y to the y to the 2 delta.
If there's no one.
If there's no 1, oh, v, and v, I'm going to bound by 1. The v is in the denominator.
And so that's
So the
fine.
difference from that and the case where they were genuinely co-prime is just this +1.
In order to get everything to work, we had to break things up and capture the v. But yes, there was no difference between the truth and the actual argument. Yeah. Okay.
So now we don't have.
So let's look at the pieces. If there's a +1, then we've saved q squared. There's no q squared. We don't save an x, but we save a q squared. This saves
I see.
q squared, and it also saved this y to the 2 delta. And in this setting, we don't save any q's, but we save an x. This saves 1 over x, and it saves x. It saves x. It has an extra factor of 1 over x. It saves x and a 1 y to the 2 delta. In either case, we should be good. Okay, let's put everything together.
+1 didn't break the argument.
The +1 did not break the argument in this case.
And you're saying that there are times that arguments, nice arguments break
There are beautiful proofs of RH
using.
that
Miss that
when you
+1.
put the +1 back in, fall completely apart. Okay, if you estimate things too precisely,
That's subtle.
it's very subtle, and it's a very common mistake, which is why I keep hammering it.
Do renowned mathematicians make this sort of
Yes.
mistake? Oh, boy.
Wait, what proof do you have in mind?
Let's talk offline.
Okay.
Yeah,
It makes me think of like the equidistribution of fairy points or something.
that's one, that is definitely one approach. Yep. Yep, you get
Okay.
that to a large accuracy and you prove RH.
Uh-huh.
And if you want to count things in intervals and you do it and you think you're doing it extremely precisely, but you're missing a +1, then it ruins everything. Yep.
Uh-huh.
Yeah, already in sieve theory. Okay, we'll get to
Post discussion, post class discussion.
yeah. But this is the exactly the thing that happens in the naive sieve versus the basic Brun sieve. Okay, Lewis knows what I'm talking about, but let's come back to that. Let's just finish this. Where are we? Where are we? All the way back to this sum. So we have this sum squared, we have this x to the 2 delta x squared. Let's start with that. What have we proved? We have that the sum over q of size q, a coprime to q, r hat n theta squared is bounded by, let's be crude, x to the 2 delta times x squared. And then there's going to be three contributions. One contribution is
Not
this.
zero, okay, yeah.
So this is a q and a y to the 4 delta.
Yeah.
Up to n to the epsilons. So I'll put an n to the epsilon just in front of everything. There's a q. Okay, let me write it like this. Q and a y to the 4 delta. That's one contribution.
Then you have the relatively prime
Yes.
phase.
So I'll say y to the 2 delta, q to the 4 over x, y to the 2 delta, q to the 4 over x.
Which coincides with the back of the envelope.
Yes. And a y to the 2 delta q squared.
This is dominated by.
Yeah, so let's get our bearings on everything. There's this end of the epsilon sitting everywhere. I'm going to write this x to the 2 delta plus 2 as x to the 4 delta. And I'm going to pull out a y to the 4 delta. So now I get n to the 4 delta. Okay, which is exactly the trivial bound on this. N to the 4 delta.
How did we do this again?
Well, I haven't finished what has to happen. I'm pulling out a y to the 4 delta from here,
Oh, from there, okay.
and from here, which means I have a y to the 2 delta denominator, and from here, which means I have a y to the 2 delta denominator. And this, I'm replacing x to the 2 by x to the 2 delta. So I have to multiply in an x to the 2 times 1 minus delta. X is n to the 3/4, right? So this is n to the 3/2 times 1 minus delta.
Yes. Wait, and then with the x to the 2 delta, how did we convert that into an n?
X times y.
The x to the 2 delta I turned into an x squared. I turned into an x to the 2 delta. Oh, how did the x to the 2 delta plus a y to the 2 delta is x times y is n.
Oh, I see.
So when I have an x to the 4 delta and a y to the 4 delta, that's an n to the 4 delta.
Okay, yeah.
Okay. And the trivial bound again is q to the 4 because I have q squared terms squared. So q to the 4. Okay. What has happened here is a 1 over q cubed. Exactly what we said we saved. Right? What has happened here, this y to the, so q to the 4 I pulled out. The y to the 2 delta should have been a y to the 4 delta, which means I need to put a y to the 2 delta in the denominator and then an x.
What was that?
So I pulled out a q to the 4,
Oh, you pulled out q.
but there's only a q here.
Right,
So that's
yeah.
a, and then here, same thing, there's a q to the 4 pulled out, That means,
Over T to the 2, 1
Yep.
to the delta.
exactly. Okay, so to go all the way back,
Who wins?
who wins? Let's integrate over WQK Rn hat theta squared. So it's an integral over beta of size k over n. And then the sum over q and a. Let me pull out the L infinity norm, the soup of r hat n theta over theta in WQK.
You took one of them.
One of those, yep, an L1 bound, and then the L1 bound over the second Klosterman refinement. Q of size q, a coprime to q, r hat n theta. And the soup of these.
And so could you do better if you had no soup? You did everything like without.
Yes, getting extra cancellation in beta, a third Klosterman refinement.
Right, that's what we talked about last.
Yes. And that will give you more control on how close delta needs to be to 1.
Okay, and that's how you can soften that restriction.
Yep. But as a first approximation, okay, so there's no, the beta integral just gives us k over n. This gives us an n to the 2 delta over kq. And this is exactly what we have here. So modulo factors of n to the epsilon, which I will treat this also as n to the epsilon
Right, so that's gonna disappear.
for delta near 1.
Yeah.
Okay.
Then the other deltas will turn into 1, right?
Yes, so now I have to take the square root of everything. So the square root of everything is an n to the 2 delta q squared. This term is, I'm treating as n to the epsilon, times all of these square rooted. So 1 over q to the 3/2, 1 over y to the delta x to the 1/2, and a 1 over q y to the delta. Okay,
And we need this to be smaller than the major arc?
we need this to be, yeah, we need, let me remind us here, we need for this a bound that's less than n to the 4 delta over n,
Which is what we got for,
which would be the size, yeah, that's the average value of the minor arcs.
of the major arc.
The major arcs squared averaged over n. So the major arc is n to the 2 delta over n. That squared is n to the 4 delta over n squared. Summed over n is n to the 4 delta.
Right, because
And
we're
we need less
averaging
than
for
that.
the minor arcs as well. Okay.
Yeah. Okay. The k and this k cancel. One of the q's cancels this. I have my n to the 4 over n to the 4 delta over n,
Mhm.
plus some crap. And q gets multiplied everywhere here. So q, I save a 1 over q to the 1/2. I save a q. This parameter is q times x to the, whoops,
I read that as q to the 4, and I'm like, aren't we in trouble?
yes. This was a q squared, and the 2 got crossed out. Is that a better way? Now it's q to the chi.
No, you're good.
Okay. Y to the delta is n to the, let's turn this into n. This is an n to the 3/4 divided by 2 is 3/8
Yeah.
plus delta over 4. So 3/8 plus delta over 4 is 3 plus 2 delta over 8.
Oh, so that's why, so this is where we're gonna see that we have to push delta in year 1 to
Uh,
make this all work out, or?
It's here. We only saved a q as long as this, these factors are smaller than q.
Oh,
And here we save a 1 over n to the delta over 4. The q multiplies the 1 over q. Okay, so this is always savings. Now q is bounded by root n.
Yeah.
Q is bounded by n to the 1/2. So in the end, we get n to the 4 delta over n
5/8 is roughly what that denominator is.
Exactly. This is 5/8 and the numerator is 4/8.
Barely saved.
So we just barely saved. This is an n to the 2 delta minus 1 eighths. And this is an n to the delta over 4. It doesn't matter what it is. This is
And that
savings.
middle guy, where did the middle guy come from? It came from the
The
back
middle-
of the envelope. computation.
Yes, the middle guy is the 1 over x savings. And then the last guy is the q squared savings.
And you're saying in practice, and really the problematic one is the 1/2 to the 1/2? The first term out of those three,
This,
is that gonna be the problematic?
well, it's not problematic. It's telling us that, again, we're in this range where here's alpha and here's kappa. This is a half. This is a half. We have major arcs over here at alpha 0, kappa 0. The L infinity bound gave us what we needed here. And now, as long as q is small, as long as q is at least something. So as long as
Right.
q is at least some q0, which is n to the alpha 0, and delta is close enough to 1,
Oh, I see, I see.
this is indeed savings. So that's this range.
That's what's gonna determine the sweet spot for our major arc.
Yes.
sort of,
Exactly. All right. That's it. I mean, that's it. And then 60 more pages of technicalities to get it to work.
But then, why, right, where's the most immediate source of technicalities coming from, right? Because you have to introduce a cascade,
Yes. Well, we haven't talked about the major arcs at all.
right?
So the question is, do we want to talk about the major arcs? Let me propose something, which would be a major arcs calculation, not in this setting, because in this setting, we really would need to develop, well, I mean, we need a whole course on thermodynamic formalism, then we need a whole course on spectral gaps. But I think I can give,
And
In-
all that went into the major arcs?
not in this problem. Oh, yes, and all of that went into this problem. Yes, exactly. But what we can do is instead, I can give you something closer to the spectral theory of automorphic forms, but soft spectral theory without doing the trace formula, just using an abstract spectral decomposition. There is a way to give you a flavor of what a major arcs calculation would look like.
Hmm. Interesting, so sort of like a generic sort of.
In the
major
same-
arcs kind of
Yeah, in the same way that this is a flavor of what a minor arcs analysis, there's the kinds of techniques that might go into a minor arcs analysis, should you face one out in the wild. You have some experience now with how to think about these things,
So
where
when
you can look for
did it with
cancellation.
Bourgain, you did say kappa big, then you did kappa small but alpha big.
Yes,
You saw exactly, what it is that you could squeeze out of that, and then you're like, now we have to make the major arcs work. Is that like the way it went?
sort of. So
Involved back and forth between them.
what really happened is that we wrote it before our Zaremba paper. We wrote a paper in 2000, God, I don't even know, 2010 or something, which was exactly this argument, and used the spectral theory to give this alpha 0 and kappa 0 region. And then after we wrote that paper, somebody said, this smells like Zaremba's conjecture. And we said, what the hell is Zaremba's conjecture? In fact, it was Kurt McMullen who told us about it. But then I went back to earlier emails, and I had done previous work on circle packings, and Jeff Ligarius said, this is similar to Zaremba's conjecture. And I glanced at Zaremba's conjecture, I couldn't make heads or tails of it. I forgot all about it. So anyway, things sometimes get planted in your head long before you're ready to hear them. And then later, and then you think you have this great original idea, and then it turns out, no, it's Jeff Ligarius that gave you that idea. Right, so Ligarius told me about Zaremba, I didn't listen. Then Kurt McMullen, again, and when we proved this theorem, in the group case, he said, isn't this like Zaremba? And so then we
Wait,
looked at
how were
Zaremba.
you doing this without Zaremba to begin with?
We were just looking at what that first paper, the first paper with Bergan. So this is Bergan
We're not using so heavily the setup, right?
We're not using so heavily the setup.
That was
Yeah,
what I was gonna ask, what's the more general?
Yes.
thing you could say?
yes. So we had a subgroup of SL2Z with dimension near one, then delta near one, and no parabolics.
Okay.
Okay, and this is an actual subgroup, not just a subset. And then we showed that if you look at the values V gamma W for your favorite fix these, the set of these values satisfies a local global, a density one local global principle. These values satisfy density one.
What does that mean? More
Local
precisely
global.
again?
So again, the local global is whatever mod Q restrictions come from gamma.
Right. And
Are
the global
from strong-
statement is which one?
And the global statement is that every sufficiently large number, or almost every, i.e.,
What does number mean? I guess is the-
it's just the values of, it's just integers that
Oh,
are
right,
values.
You're getting integers out of the inner product.
Out of the inner product.
And then you're saying,
Yeah. So for example, you take the 1 entry or something. Take the matrix coefficients of these matrices, i.e. the set of upper left entries, the 1 entries of gamma, despite not knowing anything about gamma. It's some thin, finitely generated subgroup. This is some potentially thin subgroup. Group. The set of 1 entries of gamma, well, satisfy this density one local goal principle. In other words, the number of these, number of such up to n divided by the number of admissibles up to n. Admissible up to n goes to 1, exactly.
and then like, what was our set up for Zaremba? Here we were taking our gamma was,
Semi-group.
Was a semi-group instead of a group, but we already had this experience.
oh, and then the semi-group was it was just breaking up the matrices for the
Yes,
continued fraction.
Exactly.
decomposition.
exactly. So we already had a plan of attack. The problem was to get it to work.
Mm.
And so the first thing we did is we proved positive proportion. And that was by continuing to break this up into more and more pieces all the way down to constant size.
That's a cascade.
That's this cascade, yeah. So that's why we needed pieces at all orders. And then we realized if we take one of the pieces and we do a little bit of this thermodynamics and spectral theory, then we'll get density 1. So that was, in the end, how the argument went.
So why did the other person say that this looks kind of like Zaremba? It was the connection between Zaremba and the semi-group, was all of that kind of known? We did some work to get Zaremba into a form where we can actually approach it this way.
These are elementary.
Or is that, no, okay.
I mean, those observations are elementary.
Okay.
How to make use of them. I guess we were the first to observe that there are a lot of tools that can be made to work in these settings on this problem.
I mean, if you extend this paper to say that gamma is a semi-group,
Yes.
then you have it for free, right? Or not?
Well, that was the hard part. Extending from groups to semi-groups was the hard part.
I'm just saying that all we're doing is probably applicable for semi-groups.
Yes. Oh, yes. There. So everything is applicable. Well, you mean what's the general setting in which this argument applies? We did use some. We used the fact that it has no parabolics.
Yeah.
We used the fact that.
How the dimension close to 0, close
Yeah.
to 1, no parabolics, semi-group.
Yeah.
And this is enough.
To get this density 1. Yeah. But just to show you, so this is with the bilinear form V gamma W. But if you look at, so here's a problem. Instead of the map that sends gamma to V gamma W, where we know this, so replace this by gamma goes to trace. So instead of, I mean, on the level of individual elements, replace this by
Yeah.
Gamma goes to the trace. It's still a linear map. Everything else is supposed to go through. No parabolics, whatever you want, delta near 1, delta equal to 1. We still don't know a positive proportion in this setting. Don't
Does
know.
this give something fancy? Because I mean, this theorem, if it wasn't for the Zaremba conjecture, I would feel no closeness to it. Do we have a closeness for this trace of gamma?
So there's a recent paper of Xinjiang and myself, where we produced a density 1 set of traces in these semigroups. The traces control the lengths of closed geodesics on the surface H mod gamma.
The length of close to this.
Yes, this is our next topic.
Okay, but
These-
but when you say the length,
These traces control,
Oh, because
So-
we're gonna talk about the class number.
yeah, you have some quotient, whatever it looks like, and you look at closed geodesics. You have some closed geodesic, the length of that closed geodesic, people are very interested in the length spectrum and the set of lengths. The trace of a matrix controls the length
Yeah.
of the corresponding closed geodesic.
and if we have this density 1 business, what will it give us for the length?
It'll explain to us, well, if we have the full local global, it'll tell us sort of everything we have the right to know about the length set. The set of lengths of closed geodesics on these subgroups that otherwise we don't know anything about. So there's a recent paper of myself and Xin Zhang